There were periods in Earth's history when ice did not stay near the poles. It moved outward, farther and farther, until glaciers reached regions that today sit beneath tropical sunlight. In rocks formed near what was once the equator, scientists have found scratches carved by moving ice. Stones dropped from melting glaciers lie embedded in sediments that should have formed in warm seas. Something happened. The surface brightened as ice spread. Sunlight reflected back into space instead of warming the ocean. The planet cooled further. Ice advanced again, and this did not happen just once. These frozen intervals occurred long before forests, long before animals, long before complex ecosystems reshaped the land. The sun was dimmer then, life was microscopic, the atmosphere was different. Ancient rocks record abrupt shifts, carbon signatures change suddenly. Glacial deposits are capped by layers of carbonate, marking rapid thaw after deep freeze. During at least one of these events, Earth may have come close to becoming entirely encased in ice, a world still orbiting the sun, still receiving light, yet locked in cold. How does a planet freeze so extensively while circling a star? How did life survive beneath a frozen ocean? And how many times did Earth tip into this white stillness? Tonight, we step toward those frozen chapters in Earth's history, guided only by what the rocks still remember. If these quiet journeys into deep time bring you comfort, you're welcome to leave a like or subscribe. And if you feel like sharing, tell me where you're winding down from and what time it is there. It's always remarkable to see how far these explorations travel. Now take a slow breath, let your shoulders soften, and let's move back to a time when ice began to spread across the world. Cold is not a single condition on a planet. It arrives in layers, in degrees, in quiet rearrangements of water and light. When scientists speak of an ice age, they do not imagine a world entirely seized by frost. An ice age is a long interval in which permanent ice exists at the poles, waxing and waning across thousands of years, advancing and retreating with slow orbital rhythms. Within such an age, glaciers breathe in and out across continents, seas lower and rise, forests migrate, and life adjusts without the planet ever surrendering wholly to white. By that measure, Earth is still living inside an ice age. Vast sheets of ice rest upon Antarctica and Greenland, enduring through seasonal cycles and longer climatic pulses. The world feels temperate to those who walk beneath blue skies, yet deep cold persists at the poles as a defining feature of the era. What shifts within this broader state are glacial and interglacial phases, intervals of expansion and retreat, shaped by subtle changes in Earth's orbit and tilt. These fluctuations are dramatic in human terms, but they leave oceans open and tropics warm. They do not approach planetary stillness. An ice world, in contrast, describes something far more comprehensive. It refers to episodes when ice did not remain confined to high latitudes, but spread toward the equator, perhaps reaching seas that now lie beneath tropical sunlight. In these intervals, glaciers carved landscapes near regions that today host deserts and rainforests. Geological traces suggest that frozen conditions touched latitudes once thought immune to such severity. The image shifts from polar caps to a globe where brightness dominates most horizons. This possibility is framed most boldly in the Snowball Earth hypothesis. According to this idea, ice sheets expanded until oceans themselves were sealed beneath thick crusts, and the reflective surface of ice amplified the cooling. When sunlight strikes open water, much of its energy is absorbed. When it strikes ice, much is returned to space. This simple contrast sets in motion what scientists call ice-albedo feedback. More ice reflects more sunlight. Reflected sunlight lowers temperature, Lower temperature allows ice to expand further. The loop strengthens itself, turning incremental cooling into sweeping transformation. Under certain conditions, the feedback becomes powerful enough to push the climate toward extremes. What makes equatorial ice so striking is the expectation that the tropics should serve as thermal anchors. They receive the most direct sunlight, the steadiest influx of solar energy. To find evidence that glaciers once operated at sea level near the equator challenges assumptions about how stable that energy balance must be. It implies that Earth's climate system, governed by atmosphere, oceans, and continents, can reorganize so profoundly that even regions bathed in sunlight cannot resist the spread of cold. Yet the picture is not settled in every detail. Some researchers envision a complete freeze, oceans capped from pole to pole. Others propose a slush ball state, with belts of open water persisting near the equator, allowing limited exchange between ocean and air. Rocks provide clues, but interpretation requires careful reconstruction of ancient geography and chemistry. Models simulate possibilities, adjusting reflectivity, greenhouse gases, and continental positions to see how far the cooling might go. Each line of evidence adds weight, but also nuance. An ice world, then, is not merely a colder version of today. It is a reconfiguration of the entire climate system, a state in which feedbacks reinforce one another until the familiar gradients between pole and tropic flatten into a stark simplicity of ice and reflected light. The distinction matters because it frames the scale of what Earth has endured. Between the ordinary pulses of an ice age and the vast stillness of global glaciation lies a difference not just of temperature, but of planetary character. Long after the ice withdrew, it left behind a quiet archive. Not in words, not in monuments, but in stone laid down grain by grain, layer upon layer, waiting for patient hands to notice what did not quite fit. The story of frozen oceans and wandering glaciers is written there, scattered across continents that were once joined in unfamiliar arrangements. In Namibia, Australia, and Canada, geologists have uncovered thick sequences of sediment that bear the unmistakable signature of glacial transport. These deposits contain fragments of rock too large and too angular to have been carried by ordinary rivers. Some are embedded within fine marine mud, as though they fell from above into calm water. These stones, known as drop stones, reveal a subtle drama. Icebergs drifting over ancient seas would have carried debris locked within their frozen bodies. As the ice melted, the stones dropped through the water column and sank into soft sediment below. Around each fallen fragment, the surrounding layers bend slightly downward, preserving the moment of impact in a small distortion of mud that later hardened into rock. Elsewhere, broad surfaces of ancient bedrock display parallel grooves etched into their surfaces. These striations run in consistent directions, carved by the slow movement of ice sheets dragging stones across solid ground. The scratches are not random, they align with reconstructed paths of glacial flow, extending across landscapes that today lie far from any persistent ice. Their presence speaks of weight and motion sustained over long intervals, of pressure immense enough to reshape continents. The evidence grows more compelling when the position of these rocks in deep time is considered. Through the study of paleomagnetism, scientists measure the faint magnetic signatures locked within minerals as they crystallized. When certain rocks form, especially volcanic or fine sedimentary layers, tiny magnetic grains align with Earth's magnetic field. That alignment becomes fixed as the rock solidifies. By analyzing the direction and inclination of these magnetic patterns, researchers can estimate the latitude at which the rock originally formed. In several of these glacial sequences, the magnetic signatures indicate formation near the equator. The implications are profound, yet measured, suggesting that ice once operated in regions that would ordinarily receive abundant sunlight. Chemical clues deepen the narrative. Layers deposited immediately after these glacial intervals often display dramatic shifts in carbon isotopes. The ratio of different forms of carbon within the rock changes sharply, implying disturbances in the global carbon cycle. Such anomalies hint at a world where photosynthesis and ocean chemistry were profoundly altered, consistent with widespread ice cover disrupting normal exchange between atmosphere and sea. Above many glacial deposits rests a distinct geological layer known as cap carbonate. These pale carbonate-rich rocks sit abruptly atop glacial sediments, sometimes forming thick, laterally extensive sheets. Their composition and texture suggest rapid precipitation in warm carbon dioxide-laden waters. The contrast between the coarse debris of glacial origin and the smooth, chemically precipitated cap is striking in the field, a boundary that marks swift climatic transformation recorded without commentary, only in mineral form. Each of these lines of evidence, taken alone, might allow for alternative explanations. Together, they interlock. Striated bedrock indicates moving ice. Dropstones confirm floating glaciers over open water. Magnetic signatures anchor these events to tropical latitudes. Isotopic excursions reveal global chemical upheaval. Cap carbonates testify to dramatic aftermath. The rocks do not proclaim their meaning loudly, but their consistency across continents builds a coherent case. What emerges is not a single outcrop speaking in isolation, but a planetary pattern distributed through deep time. The archive is fragmented by erosion and tectonics, yet enough pieces remain aligned to suggest that Earth once entered states far colder and more expansive than any recent memory. In the patient language of geology, credibility accumulates slowly, layer upon layer, until the silence itself feels structured. Before the long silence of advancing ice, the planet moved through a very different balance, one that feels distant even when imagined slowly. In the Paleoproterozoic world, more than 2 billion years ago, Earth was neither barren nor familiar. It occupied a middle state, shaped by forces that would later shift, but for a time held steady in a fragile warmth. The sun above was dimmer than it is now, radiating less energy across the inner solar system. By modern expectations, that fainter light should have left Earth colder, perhaps locked in frost from the beginning. Instead, the atmosphere compensated. It carried abundant greenhouse gases, most notably methane, which gathered in concentrations far higher than those known today. Methane is efficient at trapping heat. Even under a weaker sun, this invisible blanket absorbed outgoing infrared radiation and retained warmth near the surface. The sky itself may have carried a hazy tint, organic particles forming high in the atmosphere as methane reacted with sunlight, filtering the pale day into softer tones. The oceans below were not empty. They teemed with microbial life, especially cyanobacteria and other simple organisms that thrived in shallow waters. These communities formed layered mats along coastlines and continental shelves, building delicate structures that trapped sediment and altered chemistry. They were the primary engineers of the biosphere, shaping both the composition of seawater and the gases exchanged with the air above. There were no forests leaning toward the light, no animals crossing beaches, no roots gripping soil. Life existed almost entirely in microbial form, low to the ground or suspended within water, invisible from a distance, yet powerful in cumulative effect. Continents during this era bore little resemblance to their present outlines. Cratons, the ancient cores of today's landmasses, were assembled in configurations that have long since dispersed. Supercontinents rose and fragmented, altering patterns of ocean circulation and weathering. Mountain belts eroded under rainfall that carried dissolved minerals back to the sea. Volcanic arcs traced shifting plate boundaries, adding carbon dioxide to the atmosphere in slow pulses. The surface was dynamic, even if its inhabitants were microscopic. Greenhouse gases maintained the overall equilibrium. Carbon dioxide released from volcanoes mixed with methane, produced and sustained by microbial processes. Chemical weathering of exposed rock consumed some of that carbon dioxide, binding it into minerals that would later become limestone. The balance between volcanic input and weathering removal acted as a thermostat, though one less finely tuned than in later eras. Methane added an additional layer of insulation, compensating for the faint sun and preventing the oceans from freezing solid. Within this state, warmth was not uniform, but sufficient. Shallow seas remained liquid, allowing microbial ecosystems to expand. Nutrient cycles operated at a pace set by the chemistry of rocks and water, not yet accelerated by complex organisms. The atmosphere was largely devoid of oxygen, and iron dissolved freely in seawater, waiting for conditions that would later change its fate. The planet's systems interacted quietly, exchanging energy and matter across boundaries that were stable for millions of years at a time. This was the backdrop against which future disruption would unfold, a world stabilized by methane and carbon dioxide under a gentler sun. Its equilibrium depended on delicate feedbacks between geology and life, feedbacks that had not yet been tested by dramatic shifts. The warmth that seemed secure in this era rested on conditions that could be altered by the very organisms sustaining it, and the quiet oceans carried within them the seeds of transformation. The transformation did not arrive with noise or flame, but with a molecule. Oxygen, invisible and highly reactive, began to accumulate in a world that had long existed without it. The architects of this change were the same microscopic communities that had quietly dominated the shallow seas, harvesting sunlight and splitting water as part of their metabolism. In doing so, cyanobacteria released oxygen as a byproduct, at first in modest quantities, that were quickly absorbed by surrounding chemistry. For millions of years, this newly produced oxygen did not linger in the air. It reacted readily with substances abundant in the oceans and crust. Dissolved iron, once stable in oxygen-poor waters, combined with the rising gas to form iron oxides that settled to the seafloor. Layer upon layer, these reactions built banded iron formations, striking geological records composed of alternating red and dark bands. Each band reflects a pulse of oxidation, followed by quieter intervals, a chemical rhythm imprinted across continents. The oceans gradually lost their store of freely dissolved iron, and the sinks that had consumed oxygen began to saturate. As those sinks filled, oxygen started to escape into the atmosphere in more persistent amounts. Its presence altered the balance of gases that had maintained warmth under a dimmer sun. Methane, once a powerful greenhouse blanket, proved vulnerable in the new conditions. Oxygen reacts with methane in the upper atmosphere, breaking it down into carbon dioxide and water. Carbon dioxide still traps heat, but far less efficiently molecule for molecule. The gradual erosion of methane reduced the atmosphere's insulating strength, thinning the protective layer that had compensated for weaker solar output. The shift unfolded over spans difficult to imagine, yet its consequences accumulated. With methane diminished, the greenhouse effect weakened. Surface temperatures began to drift downward. Feedbacks that once sustained warmth no longer operated with the same stability. The atmosphere, enriched in oxygen, marked a departure from its earlier chemical identity, and the climate system adjusted in response to this internal restructuring. At the same time, oxygen reshaped biological possibilities. It introduced both opportunity and stress. For organisms adapted to an oxygen free world, the gas could be toxic. Some retreated to environments where oxygen remained scarce. Others evolved mechanisms to tolerate or even exploit it. The biosphere was undergoing a profound reorganization, though its most visible effect would emerge not in diversity, but in climate. This interval, known as the Great Oxygenation Event, stands as a pivotal threshold in Earth's history. It represents a moment when life altered planetary chemistry on a global scale. By reducing methane concentrations, the oxygenation of the atmosphere may have nudged the climate toward instability. Geological records point to a series of prolonged glacial episodes beginning roughly 2.4 billion years ago, collectively referred to as the Huronian glaciations. Ice expanded across large portions of the planet, and temperatures dropped significantly compared with the preceding era. The connection between rising oxygen and the onset of these glaciations remains a subject of careful study, but the timing aligns in compelling ways. A biosphere that had long acted as a stabilizing influence through methane production instead shifted the atmospheric balance in a different direction. Life, in transforming its environment, inadvertently set the stage for colder conditions. In this convergence of biology and climate, the planet's history turns inward. The trigger for widespread cooling did not originate solely from volcanic force or orbital drift, but from microscopic cells engaging in routine metabolism. The oxygen they released accumulated patiently, altered atmospheric chemistry, and weakened the greenhouse effect that had shielded early Earth from deep cold. Within that quiet chemical revolution lay the possibility of the first major global freeze, a reminder that even the smallest organisms can redirect the trajectory of an entire world. Across a span stretching from roughly 2.4 to 2.1 billion years ago, the rock record begins to speak in a colder dialect. Layers from this interval, preserved on several ancient cratons, reveal repeated advances of ice that far exceeded any fleeting climatic fluctuation. This era, known as the Huronian glaciations, marks the first prolonged descent into conditions severe enough to reshape the planet on a planetary scale. The duration alone sets it apart. The Huronian was not a single frozen episode, but a sequence of glacial pulses unfolding over nearly 300 million years, punctuated by intervals of partial retreat. Ice advanced, withdrew, and advanced again, as though the climate system were oscillating around a newly unstable equilibrium. Each pulse left behind distinct sediments, recording cycles of expansion and contraction that spanned timescales, dwarfing the history of complex life. Geological evidence from Canada's Superior Province, along with correlating strata in southern Africa and other fragments of ancient crust, indicates the presence of extensive ice sheets. Some deposits suggest glaciers reached sea level, interacting directly with marine environments. Diamectites, unsorted mixtures of clay, sand, and large stones, testify to the grinding force of ice moving across landscapes and depositing debris without the sorting action of rivers. These sediments appear in contexts that imply wide geographic distribution, raising the possibility that ice cover was not confined to polar regions alone. Whether the Huronian achieved a fully global freeze remains uncertain. The available evidence allows for scenarios ranging from widespread continental glaciation to a more expansive state approaching near global conditions. Paleomagnetic data and sedimentological clues offer hints, But the picture is incomplete, blurred by tectonic recycling and the immense age of the rocks involved. Some researchers envision broad ice coverage across multiple continents with open belts of ocean remaining. Others consider the possibility that ice extended close to equatorial latitudes. The debate reflects the fragmentary nature of the archive rather than a lack of seriousness in interpretation. For the microbial biosphere, these long intervals of cooling imposed new constraints. Shallow marine habitats, previously expansive and sunlit, likely contracted as ice encroached and sea levels shifted. Photosynthetic communities would have adapted to altered light penetration and changing chemistry. In colder waters, metabolic rates slow and ecological interactions reorganize. Yet evidence of continued biological activity during and after these glacial intervals suggests that life endured, adjusting to harsher conditions rather than vanishing outright. The chemical signatures of this time also imply fluctuations in atmospheric composition, consistent with the recent rise in oxygen and the decline of methane-driven greenhouse stability. Reduced greenhouse forcing would have made the climate more susceptible to feedbacks favoring ice expansion. Volcanic outgassing continued beneath the surface, releasing carbon dioxide that accumulated over time, potentially contributing to episodic warming between glacial pulses. These long-term interactions between atmosphere, ocean, and crust created a dynamic pattern rather than a single static freeze. Humility is necessary when describing events so distant. Much of Earth's early crust has been altered or erased, and reconstructions rely on surviving fragments stitched together through careful comparison. The Huronian glaciations stand as the earliest strong candidate for an ice world phase, yet the degree of completeness in ice coverage remains a matter of ongoing investigation. What is clear is that Earth entered a prolonged interval of climatic severity, unlike the balanced warmth that preceded it. Within these hundreds of millions of years, the planet experienced repeated episodes of ice expansion that reshaped surface environments and tested the resilience of its simplest inhabitants. The Huronian did not represent a brief anomaly, but a sustained chapter of instability, written in stone and chemistry, marking the first great cold threshold in Earth's deep history. Climate can change gradually, almost imperceptibly, until it crosses a threshold where the rules begin to reinforce themselves. In the earlier warmth of the Paleoproterozoic, greenhouse gases buffered the planet against the faint sun. Later, as atmospheric chemistry shifted, that buffer weakened. What followed did not require a sudden catastrophe, only a small imbalance that began to amplify its own consequences. Ice is bright. Compared with open ocean or dark land, it reflects a large portion of incoming sunlight back into space. This property, known as albedo, determines how much solar energy is absorbed at the surface. When snow or ice expands across a region, less energy is retained there. Temperatures fall slightly, sometimes only by a fraction of a degree at first. Yet that slight cooling allows ice to persist longer through seasons that would otherwise melt it, and to extend into areas that previously remained unfrozen. As the reflective surface grows, more sunlight is returned to space. The reduction in absorbed energy cools the air and water further. Cooler conditions support additional ice formation, both on land and across the oceans. What began as a modest expansion becomes a reinforcing cycle. Each increment of ice encourages the next. The feedback does not require intention or direction. It emerges naturally from the physics of light and phase change. In temperate conditions, this loop can stabilize. Warmer intervals interrupt ice growth, melting snow before it spreads too far. However, under a weakened greenhouse effect and a dimmer solar output, the balance can tip. If ice reaches lower latitudes, it begins to intercept sunlight that would otherwise heat the most energetically significant parts of the planet. The tropics normally act as anchors of warmth, redistributing energy toward higher latitudes through atmospheric and oceanic circulation. When reflective surfaces intrude into these regions, the redistribution weakens. The entire climate system becomes more susceptible to further cooling. Sea ice adds another layer to the process. Open water absorbs sunlight and stores heat, releasing it gradually. Once a continuous sheet of ice forms, that exchange slows. Beneath the frozen surface, the ocean becomes insulated from the atmosphere, and heat from below has limited influence on surface temperatures. The bright cap above continues to send solar radiation outward. As seasonal cycles repeat, the persistence of ice increases the likelihood that even brief warm intervals will fail to reverse the trend. This progression illustrates what scientists describe as a positive feedback loop. The term does not imply benefit, it refers to amplification. A small initial change produces effects that strengthen the original shift. Cooling leads to ice. Ice enhances reflection. Reflection leads to more cooling. Given sufficient time and favorable background conditions, the loop can become dominant over stabilizing influences. Runaway freezing does not occur instantaneously. It unfolds across thousands or millions of years, each cycle of cooling and expansion building upon the previous one. Volcanic outgassing continues beneath the surface, and carbon dioxide still accumulates gradually, but its warming influence may lag behind the rapid increase in reflectivity. The system enters a state where loss of absorbed sunlight outweighs the heat retained by greenhouse gases. In such a state, the planet does not simply grow colder, it reorganizes. Energy gradients flatten, circulation patterns shift, and ice sheets push outward in slow motion. The transition may appear subtle within a single human lifetime, yet in geological terms it marks a decisive pivot. A world that once balanced warmth through atmospheric chemistry can, through the quiet arithmetic of reflected light, lock itself into a prolonged embrace of ice. Beneath an unbroken ceiling of ice, the ocean does not vanish, it changes character. The surface, once stirred by wind and warmed by sunlight, becomes sealed under a rigid lid that can grow hundreds of meters thick in places. Snow accumulates above, compressing into denser layers, while the boundary between ice and water remains sharply defined yet slowly shifting. Pressure from accumulating ice lowers the freezing point slightly, and salt expelled during sea ice formation increases the density of underlying waters. Stratification deepens, and the vertical exchange that once connected atmosphere and sea weakens into near stillness. Light fades quickly. Even clear ice absorbs and scatters much of the incoming radiation, and any overlying snow thickens the barrier. In the upper meters of the ocean, illumination dwindles to a faint bluish glow, then to darkness. Photosynthetic organisms that once relied on abundant light at the surface face a severe constraint. Primary productivity, the foundation of marine food webs, contracts dramatically. In a fully sealed ocean, surface photosynthesis may collapse across vast regions, altering the chemistry of the water and reducing the flux of organic carbon to deeper layers. Some researchers propose that the freeze may not have been absolute everywhere. The slushball hypothesis suggests the possibility of a narrow equatorial belt where thinner ice or seasonal openings allowed limited exchange with the atmosphere. In such regions, sunlight could penetrate more effectively, sustaining pockets of productivity. The existence and extent of these open waters remain debated, yet even intermittent exposure would provide critical refuges for microbial communities, enabling some continuity in global biogeochemical cycles. Far below the ice, the deep ocean retains a different source of energy. Hydrothermal vents along mid-ocean ridges continue to discharge mineral-rich fluids heated by Earth's interior. These vents create localized environments where chemosynthetic organisms derive energy not from sunlight but from chemical gradients. Even during extensive surface freezing, such ecosystems likely persisted. The circulation of heat from below prevents the ocean from freezing solid at depth, maintaining a liquid interior despite a frozen exterior. Thermal energy rising from the mantle thus becomes a quiet counterpoint to the reflective chill above. Chemical processes within the ocean shift as well. With reduced photosynthesis, oxygen production declines in surface waters, while respiration and decay continue where organic matter is available. Redox gradients sharpen and the distribution of dissolved gases changes. Isolation from the atmosphere limits replenishment, allowing regional depletion or accumulation of certain compounds. Nutrient cycling slows and reorganizes, potentially concentrating elements in specific layers. The ocean becomes less dynamic in its upper reaches, more stratified, more internally governed. In shallower areas where ice grounds onto continental shelves, pressure and abrasion reshape coastal environments. Yet beneath the ice cover itself, water remains fluid, moving slowly under pressure gradients and density differences. Tidal forces still exert influence, generating subtle currents that prevent complete stagnation. Even in deep freeze, the ocean retains motion, though greatly muted compared with open water conditions. Within this subdued world, life contracts into refuges defined by chemistry and heat rather than sunlight. Microbial communities adapt to diminished energy inputs, persisting in protected niches where minimal light penetrates or where hydrothermal activity supplies alternative resources. Survival does not depend on abundance, but on resilience within constraints. The ocean under ice becomes a vast, dim chamber, insulated from the sky, where processes continue at a restrained pace. Movement slows, sound dampens, and the upper waters settle into a prolonged quiet shaped by the weight of frozen surface above. Even in the deepest cold, the planet does not fall silent. Beneath frozen seas and immobile skies, tectonic plates continue their slow migration, and along their boundaries, molten rock finds paths upward. Volcanoes persist through ice-covered eras, just as they do in temperate ones, venting gases from Earth's interior in steady, unhurried pulses. Among these gases, carbon dioxide rises invisibly through fractures and eruptive plumes, entering an atmosphere that has grown increasingly reflective and cold. During extensive glaciation, one of the climate system's primary stabilizers weakens. Chemical weathering, the process by which rainwater reacts with exposed rock and draws carbon dioxide out of the atmosphere, depends on liquid water and active hydrological cycles. When large portions of the continents are buried beneath ice, and precipitation falls mainly as snow, weathering slows dramatically. Rivers become limited, soils thin, and the chemical exchange between rock and air diminishes. Carbon dioxide released by volcanoes is no longer efficiently removed. The imbalance unfolds gradually. Each eruption contributes a small increment of gas, often unnoticed against the vastness of the sky. Over thousands, then millions of years, These increments accumulate. With weathering suppressed, carbon dioxide lingers longer in the atmosphere. Concentrations rise far beyond levels typical of non-glacial intervals. The greenhouse effect strengthens in proportion, trapping additional outgoing infrared radiation. Surface temperatures respond slowly at first, moderated by the high reflectivity of widespread ice. Yet the accumulation continues. Volcanism does not depend on surface climate. It is driven by heat from deep within the mantle and by plate motions that proceed regardless of ice cover. As carbon dioxide builds, it thickens the atmospheric blanket. Sunlight that once met a bright frozen surface now interacts with a denser greenhouse layer that impedes heat loss to space. The energy budget begins to shift subtly. Although the ice still reflects a significant fraction of incoming radiation, the retained infrared warmth starts to counterbalance that loss. Eventually, a threshold is crossed. Rising temperatures weaken the margins of ice sheets, initiating localized melt. Darker surfaces of exposed ocean or land absorb more sunlight than ice, reducing albedo in those regions. This initiates a reverse feedback. Where melting occurs, reflectivity declines. Where reflectivity declines, absorption increases. Where absorption increases, warming accelerates. What began as a slow buildup of greenhouse gases transitions into a more dynamic phase of deglaciation. The melting may advance rapidly in geological terms. Once substantial areas of ice retreat, the climate system can flip from a stable frozen state to an equally stable warm one. Meltwater flows across continents, transporting minerals to the sea and reactivating chemical weathering processes that had long been suppressed. Carbon dioxide, once accumulating unchecked, begins to be drawn down through renewed rock reactions. The atmosphere shifts from extreme enrichment toward gradual stabilization. Evidence for such rapid reversal appears in geological sequences where glacial deposits are overlain by sediments, indicating warm conditions and intense chemical precipitation. These transitions suggest that thawing did not proceed evenly, but accelerated as feedbacks inverted. A planet locked in ice for millions of years could emerge into a greenhouse phase marked by elevated temperatures and vigorous hydrological cycles. This sequence reflects a tension embedded within Earth's systems. Ice-albedo feedback can push climate toward deep freeze, while volcanic carbon dioxide accumulates patiently beneath the surface, preparing a counterforce. The interplay between suppressed weathering and persistent outgassing eventually tips the balance. Thaw arrives not through sudden external intervention, but through internal continuity, the steady persistence of volcanic processes that never ceased. In the long arithmetic of planetary climate, patience becomes transformative, and accumulated warmth releases a world from its frozen restraint. By the time Earth approached 720 million years ago, the planet's surface was rearranging itself again, as though preparing for another experiment in balance. The supercontinent Rodinia, long assembled into a vast configuration, began to fracture. Rifts opened across its interior, and tectonic forces pulled continental blocks apart in slow divergence. New ocean basins formed between separating landmasses, while uplift exposed fresh rock to wind and rain. This breakup did more than redraw coastlines. When continents cluster into a single mass, much of their interior remains arid, distant from moderating ocean influence. As Rodinia fragmented, newly created shorelines expanded dramatically. Moist air from surrounding seas traveled farther inland, increasing precipitation over exposed rock. Rainwater, slightly acidic from dissolved carbon dioxide, interacted chemically with silicate minerals in the crust. Through these reactions, carbon dioxide was removed from the atmosphere and ultimately transported to the oceans, where it became locked within carbonate sediments. The positioning of these drifting continents amplified the effect. Paleogeographic reconstructions suggest that many of Rodinia's fragments lay near equatorial latitudes during this interval. In the tropics, solar heating drives vigorous evaporation and convection, fueling frequent rainfall. Warm temperatures accelerate chemical reactions between water and rock, increasing the efficiency of weathering processes. With large expanses of fresh, uplifted crust exposed under intense tropical rainfall, the drawdown of atmospheric carbon dioxide likely intensified. Over extended timescales, this enhanced weathering acted as a powerful climate regulator. Volcanic outgassing continued as before, but the removal of carbon dioxide through silicate weathering may have begun to exceed the rate of replenishment. Gradually, the greenhouse layer thinned. Unlike earlier intervals when methane played a dominant insulating role, the cryogenian atmosphere depended more heavily on carbon dioxide for warmth. As concentrations declined, the planet's ability to retain heat weakened. Simultaneously, the distribution of continents near the equator may have altered ocean circulation patterns. Land masses interrupt currents, redirect heat transport, and influence the exchange of energy between hemispheres. Shallow seas over continental shelves facilitate additional weathering and nutrient cycling, further coupling tectonics and climate. The integrated effect of these changes nudged the system toward cooler conditions. Cooling did not arrive abruptly. Temperatures likely drifted downward over millions of years, perhaps punctuated by shorter fluctuations. Yet, at some point, a threshold was crossed. Once ice began to expand into lower latitudes, reflective surfaces increased the planetary albedo. The feedback described earlier emerged again, this time under different continental arrangements and atmospheric composition. More reflection meant less absorbed solar energy. Reduced absorption meant further cooling. The loop began to strengthen. The Cryogenian marks the onset of what would become the most dramatic glacial episodes known in Earth's history. Geological evidence from multiple continents indicates that ice advanced to unusually low latitudes during this era. Sedimentary sequences record glacial deposits in regions that paleomagnetic data place near the equator. The scale and synchronicity of these deposits suggest a global transformation exceeding the Huronian in both extent and clarity of preservation. Underlying this transformation was the quiet arithmetic of plate tectonics and chemical weathering. Rodinia's fragmentation increased the planet's capacity to remove carbon dioxide, especially under tropical rainfall. As greenhouse concentrations declined, the climate approached instability. Once the feedback between cooling and reflection engaged, the descent accelerated. Thus, the Cryogenian began not with spectacle but with rearrangement. Continents drifted, rain fell, minerals dissolved, and atmospheric chemistry shifted. Over time, these incremental processes aligned to move Earth toward its most extreme cold state. The stage was set through tectonic motion and chemical balance, and the planet once again edged toward a threshold where ice would redefine its surface. There is a depth of time within the Cryogenian when the descent into cold becomes unmistakable. Around 720 million years ago, ice began its most expansive advance, inaugurating what is known as the Sturtian glaciation. This was not a brief interruption in climate, nor a modest extension of polar ice. It endured for roughly 58 million years, a span longer than the entire time separating the disappearance of the dinosaurs from the present day. Across that immense interval, geological records from multiple continents preserve signs of sustained glacial influence. In regions now separated by vast oceans, thick diamictite layers appear in roughly equivalent stratigraphic positions. These coarse, unsorted sediments suggest transport by moving ice and deposition in cold marine or nearshore settings. Their repetition and broad distribution point toward a coordinated climatic episode rather than isolated regional events. Paleomagnetic measurements from some of these deposits indicate that they formed at low latitudes, implying that ice extended far beyond customary polar confines. The scale implied by such evidence reshapes the imagination. Ice sheets may have spread from continental interiors toward coastlines, meeting the sea and spawning floating ice masses. If reflective surfaces reached near the equator, then the majority of incoming sunlight would have encountered a bright planetary exterior. The feedback between cooling and reflection would have deepened the freeze, sustaining it across tens of millions of years. The Sturtian, therefore, represents one of the strongest candidates for a near global glaciation in Earth's history. Marine ecosystems felt the consequences of this prolonged cold. Primary productivity at the ocean surface likely declined dramatically, especially in regions sealed by persistent ice. Nutrient cycling slowed, and redox conditions in seawater shifted as oxygen production and organic carbon export were altered. Geochemical signatures within sedimentary rocks from this period reflect disturbances in the carbon cycle, suggesting reduced biological throughput and restructured marine chemistry. Yet, evidence also indicates that life did not vanish. Microbial communities persisted in refugia, adapting to the constraints imposed by darkness, cold, and chemical change. The global synchrony of the Sturtian is particularly striking. Radiometric dating and stratigraphic correlation align glacial deposits from Australia, Namibia, North America, and other ancient cratons within a similar temporal window. While tectonic reconstructions introduce some uncertainty, the convergence of dates and sedimentary patterns supports the view that this was a planetary scale phenomenon. Such synchrony implies that the driving mechanisms operated globally, linked to atmospheric composition, continental configuration, and feedback processes, rather than isolated local factors. Throughout the 58 million years of the Sturtian, volcanic outgassing continued beneath the frozen exterior, slowly enriching the atmosphere with carbon dioxide. Meanwhile, reduced weathering under ice limited the removal of this gas. The balance between reflective cooling and accumulating greenhouse warming set the stage for eventual deglaciation, though the ice persisted for an extraordinary length of time before that reversal gained momentum. The Sturtian glaciation stands as a monument of duration and extent. It reflects a moment when the climate system settled into an extreme equilibrium that resisted change across tens of millions of years. In the layered rocks that span continents, its imprint remains coherent and expansive, suggesting that Earth once sustained a frozen state of remarkable persistence. Within that long white chapter, the biosphere endured and the planet's internal processes continued, preparing quietly for transformation yet to unfold. In the long persistence of the Sturtian cold, survival did not depend on abundance, but on subtlety. Life retreated into margins, where energy still flowed, faintly but reliably. The surface ocean, dimmed and constrained, could no longer sustain expansive microbial blooms as it once had. Yet beneath the ice, along boundaries of heat and chemistry, living systems endured with quiet resilience. Near mid-ocean ridges, hydrothermal vents continued their slow exhalations of mineral-rich fluid, heated by magma below the crust. Seawater circulated through fractures in the seafloor and returned to the ocean enriched with dissolved metals and reduced compounds. These vents created steep chemical gradients, and within those gradients, microorganisms found opportunity. Chemosynthetic pathways allowed them to derive energy not from sunlight, but from reactions between hydrogen, sulfide, methane, iron, and other molecules present in vent effluent. Entire microbial ecosystems could cluster around these sites, independent of surface illumination. In a frozen world, such environments became steady anchors, powered by Earth's internal heat rather than the distant sun. Elsewhere, beneath the ice canopy, pockets of thinner ice or localized meltwater likely formed where currents concentrated heat. Subglacial ocean regions beneath floating ice shelves may have provided narrow corridors where limited light penetrated or where tidal mixing sustained circulation. These were not expansive habitats, yet they may have been sufficient to preserve microbial communities adapted to low energy conditions. Even a minimal exchange of nutrients could support a sparse but persistent biosphere. Dormancy became another strategy. Many microorganisms possess the ability to enter states of reduced metabolic activity when resources decline. In such states, cellular processes slow dramatically. Repair mechanisms remain poised, but growth pauses. Spores or cyst-like forms can endure cold, desiccation, and chemical stress for extended periods. Within sediments or brine channels trapped in ice, dormant cells could wait for intervals of relative improvement, reactivating when conditions briefly permitted. The chemical structure of subglacial brines offered additional refuges. As sea ice forms, salt is expelled into surrounding water, sometimes creating concentrated saline channels within the ice itself. These brines remain liquid at lower temperatures than fresh water. Microbial life adapted to high salinity could inhabit these microenvironments, sheltered within a matrix of crystalline ice. The scale was minute, yet the collective persistence across countless microscopic pockets may have been significant. Stress exerts pressure not only on survival but on innovation. Prolonged environmental constraint can select for traits that enhance flexibility, tolerance, and metabolic efficiency. Genetic variation within microbial populations, combined with high reproduction rates, allows rapid evolutionary response relative to geological timescales. In the Cryogenian freeze, selective pressures likely favored organisms capable of exploiting alternative energy sources, enduring oxidative fluctuations, and maintaining cellular integrity under extreme cold. Though the world above lay silent beneath reflective ice, biochemical cycles continued in reduced but persistent form. Carbon was fixed and respired in localized domains. Nutrients cycled slowly through constrained networks. The biosphere contracted, yet it did not extinguish. Instead, it adapted to a narrower band of possibilities, inhabiting boundaries defined by heat, chemistry, and rare intervals of light. In this manner, life at the edge of global glaciation became less conspicuous yet more tenacious. Its strategies were modest, rooted in molecular adaptability rather than visible complexity. The frozen interval pressed the biosphere into secluded niches, but within those niches, evolution continued quietly. When conditions later shifted and light returned more broadly to the oceans, these survivors would not emerge unchanged. The long cold refined their capacities, shaping lineages that carried forward into a different world. After millions of years of reprieve, the climate tightened its grip once more. Around 650 million years ago, the planet entered a second cryogenian descent, known as the Marinoan glaciation. If the Sturtian had demonstrated how far ice could advance, the Marinoan appears to have tested those limits again, perhaps even exceeding them in intensity. Geological layers attributed to this interval are found across what are now widely separated continents, from Australia to southern Africa, from China to North America. In each region, thick successions of glacial sediments occupy similar stratigraphic positions, bracketed by volcanic ash layers and chemical signatures that allow precise dating. The coherence of these deposits suggests a synchronized climatic event rather than isolated regional cooling. Ice was not confined to a hemisphere or a particular ocean basin. The sedimentary record implies a planetary scale freeze. Some reconstructions propose that Marinoan ice sheets grew to immense thicknesses over continental interiors. Estimates derived from glacial erosion patterns and isostatic responses indicate that ice may have reached heights measured in kilometers in certain regions. The weight of such ice would have depressed crustal surfaces, altering local topography and influencing patterns of subglacial flow. Where ice extended over oceans, sea ice may have merged with continental glaciers, forming continuous frozen expanses that diminish the exchange of heat and gases between ocean and atmosphere. Paleomagnetic evidence from several Marinoan deposits points toward formation at low latitudes, reinforcing the possibility that glacial conditions reached near the tropics. These findings echo earlier Cryogenian signals, yet appear in sequences that some researchers interpret as representing even more severe global coverage. The Marinoan, therefore, stands as a candidate for the most extreme ice world state in Earth's history, though debates remain regarding the exact extent of open water that may have persisted near the equator. Marine sediments from this time preserve geochemical markers, indicating profound disturbance of the carbon cycle. Carbon isotope ratios shift dramatically across Marinoan boundaries, reflecting altered balances between organic carbon burial and atmospheric exchange. Such anomalies align with expectations of extensive ice cover, disrupting normal biological productivity and gas transfer. The ocean's chemistry, shaped by limited surface input and continued volcanic outgassing, likely diverged sharply from preceding conditions. Above Marinoan glacial deposits, distinctive carbonate layers appear once again, suggesting rapid warming and intensified precipitation of minerals in a greenhouse atmosphere enriched with accumulated carbon dioxide. The contrast between the diamictite layers of glacial origin and the overlying cap carbonates underscores the abruptness of climatic reversal once thresholds were crossed. In stratigraphic sections worldwide, this pairing of frozen debris below and chemical precipitate above repeats with remarkable consistency. The duration of the Marinoan glaciation, spanning roughly 650 to 635 million years ago, implies persistence over at least 15 million years, though some estimates extend its effective climatic influence further when considering transitional phases. During this span, Earth may have sustained an albedo high enough to reflect substantial portions of incoming solar radiation, reinforcing the frozen state, despite gradually increasing greenhouse gas concentrations. In the quiet accumulation of rock layers across continents, the Marinoan records an escalation of cryogenian severity. Ice advanced again, perhaps more comprehensively than before, compressing oceans and continents beneath its reflective expanse. The geological evidence, distributed globally and correlated through time, conveys a planet capable of repeating its descent into profound cold. Within these layers, the pattern of contraction and release becomes clearer, revealing an Earth whose climate system could sustain extremes before shifting once more toward warmth. There is a point in the Cryogenian record where severity reaches its quiet extreme. The Marinoan interval, already vast in duration, deepened into conditions that may represent the most complete freeze Earth has ever sustained. Geological reconstructions suggest that continental ice sheets grew to extraordinary thickness, in some regions reaching heights measured in kilometers. Such mass would have pressed heavily upon the crust, depressing it downward, altering coastlines and submerging margins beneath the combined burden of ice and sea. Across the oceans, a rigid shell of sea ice likely extended far from polar origins, where continental glaciers met frozen seas, boundaries blurred into continuous white expanses. The exchange between atmosphere and ocean slowed to a near standstill beneath this barrier. Surface winds no longer stirred open water, waves could not form beneath a continuous lid. Without direct contact with the air, the upper ocean lost much of its capacity to ventilate, and circulation patterns that once redistributed heat weakened dramatically. Ocean currents rely on differences in temperature and salinity to drive global overturning. In a world sealed by thick ice, the normal gradients diminished. Cooling at the surface became uniform across wide regions, and the insulation of ice prevented significant heat absorption from above. Deep waters may have grown increasingly isolated, their renewal slowed. The rhythm of thermohaline circulation, which in temperate eras connects equator and pole in a continuous exchange, could have been reduced to a subdued internal motion constrained beneath frozen ceilings. Above this subdued ocean, the atmosphere accumulated carbon dioxide over millions of years. Volcanic systems persisted despite the freeze, steadily releasing greenhouse gases. With large portions of the continents buried beneath ice, silicate weathering operated at a greatly reduced rate. Rivers that once carried dissolved ions to the sea diminished, and the chemical drawdown of carbon dioxide weakened. As a result, atmospheric concentrations climbed far beyond preglacial levels, though surface temperatures remained locked in cold by the planet's high albedo. The duration of this state stretched across millions of years, long enough to transform landscapes and challenge biological resilience. Ice-carved bedrock transported debris across vast distances and sculpted continental interiors. Sedimentary records preserve evidence of grounding lines where glaciers advanced into marine basins, depositing thick sequences of unsorted material. In some stratigraphic sections, these glacial layers persist over broad geographic extents, implying sustained conditions rather than brief oscillations. If viewed from space during this interval, the planet would have presented a striking appearance. Instead of the familiar contrast between blue oceans and dark continents, a dominant whiteness may have characterized much of the globe. Clouds would still have moved above the frozen surface, yet beneath them a reflective world would have returned much of the incoming sunlight back into space. The polar regions would have blended visually into mid-latitudes, reducing the gradient that ordinarily defines Earth's climate zones. In such a state, visual silence becomes an apt description. The texture of ocean swells, the shifting patterns of open water, the dark sheen of moist soil, all subdued under a mantle of ice and snow. Beneath that stillness, internal processes continued. Volcanic heat accumulated, and the biosphere endured in constrained refuges. The hardest freeze did not erase motion or chemistry, but it muted their outward expression, holding the planet in a prolonged equilibrium defined by reflective brightness and restrained circulation. The turning point did not arrive gently. For millions of years, volcanic systems beneath the crust had continued their steady exhalation of carbon dioxide into an atmosphere sealed above ice. With weathering suppressed and the surface locked in reflective stillness, that carbon dioxide accumulated to extraordinary levels. Eventually, the greenhouse effect intensified beyond the cooling force of high albedo, and the balance tipped. As atmospheric carbon dioxide concentrations rose into ranges far above those of temperate eras, infrared radiation became increasingly trapped near the surface. Even beneath expansive ice cover, incremental warming began to erode the stability of the frozen state. Margins of ice sheets thinned first, particularly in regions where ocean currents could convey subsurface heat upward. Once melting exposed darker ocean water or rock, the reflectivity of those areas dropped sharply. Absorption of sunlight increased, reinforcing the warming already underway. Deglaciation accelerated in geological terms. What had endured for millions of years began to retreat over spans, perhaps measured in hundreds of thousands to a few million years. Vast ice sheets fractured and collapsed, releasing fresh water into oceans that had long been isolated. Meltwater poured across continental surfaces, carving channels and mobilizing sediments that had been trapped beneath ice. Rivers resumed their chemical dialogue with rock, dissolving minerals at rates amplified by the high concentrations of carbon dioxide in rainwater. The greenhouse spike that initiated this thaw created intense hydrological cycles. Warm temperatures, combined with elevated atmospheric carbon dioxide, increased precipitation across newly exposed land masses. Chemical weathering of silicate rocks proceeded vigorously, drawing carbon dioxide out of the atmosphere in accelerated fashion. The flux of dissolved calcium and bicarbonate into the oceans increased dramatically, altering seawater chemistry in ways recorded clearly in sedimentary layers. One of the most striking signatures of this transition appears in the widespread deposition of cap carbonates. These carbonate-rich layers rest directly atop glacial diamectites in Marinoan sequences across multiple continents. Their textures and isotopic compositions suggest rapid precipitation from seawater saturated with dissolved carbonate species. As carbon dioxide-rich rainwater reacted with continental rocks and delivered ions to the ocean, conditions favored the formation of thick carbonate deposits in relatively short geological intervals. Ocean chemistry shifted profoundly during this transformation. Long isolated beneath ice, the marine system experienced renewed exchange with the atmosphere. Enhanced weathering delivered nutrients as well as alkalinity, potentially stimulating biological productivity in regions where light returned. Redox gradients adjusted as circulation patterns resumed and oxygen levels changed. The carbon isotope record across these boundaries reflects dramatic excursions, consistent with rapid reorganization of the global carbon cycle. The melt did more than remove ice. It reset planetary conditions. From a state of reflective stasis, Earth moved into a greenhouse phase characterized by elevated temperatures and active chemical cycling. Landscapes previously entombed beneath kilometers of ice were re-exposed to erosion and sedimentation. Coastlines shifted as sea levels rose with the addition of meltwater. The surface system reconnected with atmospheric and oceanic circulation in ways that had been muted for millions of years. This was not merely a return to prior balance. The magnitude of the greenhouse spike and the intensity of subsequent weathering introduced new chemical conditions into oceans and atmosphere alike. The transformation carved a boundary in the stratigraphic record that is both abrupt and global in its expression. The melt that followed the hardest freeze reshaped the planet's surface and chemistry, setting the stage for biological developments that would unfold in the altered environment left behind. When the ice withdrew and warmth surged across the surface, the transition did not settle immediately into calm equilibrium. Instead, the oceans entered a phase of chemical turbulence shaped by processes unleashed during deglaciation. The atmosphere, enriched in carbon dioxide during the frozen interval, interacted vigorously with rainfall and exposed rock. As precipitation intensified over newly uncovered continents, large quantities of dissolved carbon entered rivers and flowed toward the sea. The influx of carbon dioxide into ocean water lowered its pH, at least regionally and temporarily. Acidification altered the balance of dissolved carbonate species, affecting how minerals precipitated and how organisms interacted with their surroundings. Marine chemistry, long constrained beneath ice, now shifted rapidly in response to this atmospheric exchange. The carbonate deposits laid down immediately after glacial retreat testified to saturation states that fluctuated across broad geographic areas. At the same time, enhanced weathering mobilized nutrients stored within continental rocks. Phosphorus, a key limiting element in marine productivity, was released in increased quantities as chemical reactions accelerated under warm and acidic rainfall. Carried by rivers, these nutrients entered coastal waters and spread outward through ocean currents. In regions where light returned and ice-free conditions persisted, microbial populations could respond to this nutrient pulse with renewed growth. Productivity may have surged in episodic blooms, drawing down carbon dioxide locally while redistributing organic matter through the water column. These biological responses influenced oxygen dynamics. Increased productivity near the surface would have elevated oxygen generation through photosynthesis, yet the subsequent decay of organic matter in deeper waters could consume oxygen, leading to stratified conditions. In semi-enclosed basins or regions with restricted circulation, oxygen depletion might have occurred, creating pockets of anoxia. The contrast between oxygen-rich surface layers and oxygen-poor depths likely intensified before circulation patterns stabilized. Such gradients leave geochemical signatures in sedimentary records, capturing fluctuations in redox conditions across time. Phosphorus cycling became central in this reorganized system. As weathering delivered abundant phosphate to the oceans, burial rates of organic carbon may have increased. In turn, this burial could influence atmospheric oxygen levels over longer timescales, as organic carbon sequestration effectively removes reduced carbon from surface exchange. The interplay between phosphorus availability, biological productivity, and oxygen concentration established new feedbacks within the post-glacial world. Environmental instability marked this interval. Temperatures remained elevated due to lingering greenhouse conditions, while precipitation patterns were likely intense and uneven. Rapid erosion altered landscapes that had been sculpted by ice only recently. Sediment loads in rivers increased, affecting coastal habitats and marine clarity. Chemical weathering rates, initially high, began gradually to moderate as atmospheric carbon dioxide declined through mineral sequestration. The system oscillated before finding a more stable balance. In this aftermath, the oceans were not simply warmer versions of their preglacial state. They were chemically distinct, enriched in nutrients, and altered in acidity, their redox structure in flux. Microbial communities that had survived under constraint now encountered both opportunity and challenge in a transformed environment. The chemical chaos was not disorder without pattern, rather, it represented a phase of rapid reconfiguration during which geological, atmospheric, and biological processes recalibrated their relationships. From this dynamic setting, the potential for new biological complexity would gradually emerge. The shifts in nutrient availability, oxygenation, and carbonate chemistry reshaped ecological niches across marine realms. What had begun as a frozen silence transitioned into a chemically vibrant world, still settling, yet fertile with possibility as Earth continued its long recovery from the most extreme cold it had endured. In the wake of chemical upheaval and climatic extremes, the oceans settled into a new rhythm, And within that altered balance, something unfamiliar began to take shape. By the time the Cryogenian cold had fully retreated, the planet entered the Ediacaran period, a chapter marked not by ice but by quiet biological innovation. The record shifts here from microbial signatures alone to impressions of bodies large enough to leave visible traces in sediment. Across ancient seafloors, preserved in sandstone beds from Australia, Namibia, Newfoundland, and other regions, faint outlines appear. They resemble quilted discs, frond-like structures, and elongated forms arranged in radiating or branching patterns. These are the Ediacaran organisms, soft-bodied multicellular life, unlike anything seen before in the fossil archive. They lacked hard shells or skeletons, yet their size and organization indicate a level of biological complexity that exceeded single-celled colonies. The timing of their emergence follows the prolonged cycles of glaciation and deglaciation. In the transformed oceans of the post-glacial world, nutrient delivery from intensified weathering may have enriched surface waters for extended intervals. Elevated phosphorus availability and shifts in oxygen distribution created conditions more favorable for sustained multicellular growth. While direct causation remains complex, the environmental legacy of extreme freeze and rapid thaw provided a backdrop of altered chemistry and energy flow within which new forms could arise. These early multicellular organisms did not resemble modern animals in obvious ways. Some appear to have absorbed nutrients directly across their surfaces, perhaps relying on diffusion within thin body tissues. Others may have harbored symbiotic microbes that assisted in metabolism. Their internal organization suggests coordinated cellular differentiation, yet their exact affinities within later animal lineages are still debated. The fossil record preserves them as impressions and molds, silent imprints of bodies once anchored to soft sediment. Ecosystems during the Ediacaran were experimental. Instead of complex food webs dominated by active predators, communities seem to have been structured around relatively static life forms attached to the seafloor. Mats of microbial life still covered many surfaces, and the new multicellular organisms often rested upon or interacted with these microbial carpets. The boundary between microbe and macrobe blurred in some forms as colonial structures became more integrated and tissues more specialized. The gradual increase in oxygen levels during and after Cryogenian time may have supported larger body sizes and more complex organization. Oxygen allows for greater metabolic rates and supports the energy demands of differentiated tissues. In sediments from this interval, geochemical indicators suggest more stable oxygenation in at least some marine settings compared to earlier eras. Though variability persisted, the long-term trend favored environments capable of sustaining multicellular experimentation. What unfolded during the Ediacaran was not yet an explosion of diversity, but a quiet expansion of possibilities. Body plans emerged that would not endure beyond this period, alongside lineages that may have given rise to later animals. The ocean floor became a testing ground where cellular cooperation extended into larger architectures. This evolutionary dawn did not erase the memory of ice, but it grew from the conditions shaped by those extremes. The nutrient surges, altered chemistry, and oxygen fluctuations of the aftermath created a platform for complexity. Out of a planet that had endured deep freeze and rapid thaw, multicellular life stepped forward in soft outlines pressed into ancient sand, marking a new threshold in Earth's unfolding story. Not all freezes reshape the entire planet at once. Around 580 million years ago, during the later stages of the Ediacaran period, Earth experienced another descent into cold, known as the Gaskiers glaciation. Compared with the immense Cryogenian events that preceded it, This episode was shorter and more geographically limited, yet it carried significance for a biosphere already experimenting with multicellular form. The Gaskiers lasted perhaps a few million years, a brief interval by geological standards. Sedimentary records from Newfoundland and parts of western Avalonia preserve evidence of glacial deposition that can be correlated with other regions of similar age. Diamictites and associated dropstones appear within marine sequences, indicating that ice advanced into coastal basins and shed debris into seawater. Radiometric dating places this glacial interval well after the Marinoan thaw and close to the flourishing of early multicellular communities. Unlike earlier Cryogenian glaciations, the Gaskiers does not appear to have reached equatorial latitudes. Paleomagnetic data and the distribution of deposits suggest that ice coverage was extensive in certain regions, but not planetary in scale. Open ocean likely persisted at lower latitudes, and atmospheric exchange would not have been sealed beneath a continuous lid of ice. For this reason, the Gaskiers is often regarded as a severe regional glaciation rather than a full ice world state. The climate system cooled markedly, yet it did not enter the self-reinforcing albedo feedback loops that characterized Snowball Earth conditions. Even so, the impact on evolving ecosystems may have been substantial. Ediacaran communities inhabited shallow marine environments, many of which were sensitive to sea level changes and temperature shifts. Glacial advance would have altered coastlines, modified sediment supply, and disrupted established microbial mats on which some organisms depended. Cooler temperatures and increased turbidity in coastal waters could have constrained certain species while favoring others adapted to variable conditions. In the stratigraphic record, fossils of Ediacaran organisms appear both below and above Gaskiers' glacial deposits. Some assemblages show signs of ecological turnover following the event. Although preservation bias complicates interpretation, the temporal proximity between glaciation and shifts in fossil communities hints at environmental pressure shaping evolutionary trajectories. The Gaskiers may have acted as a filter, pruning some lineages while allowing others to diversify in its aftermath. The shorter duration of this freeze likely limited its capacity to reorganize global carbon cycling to the degree seen in cryogenian intervals. Chemical weathering continued in non-glaciated regions, and ocean circulation persisted where ice did not impose barriers. Thus, the Gaskiers illustrates a different mode of climatic disturbance, one that perturbs without engulfing. It serves as a reminder that not every glaciation reflects the extreme state of a snowball Earth, even when geological evidence for ice is clear. Within this moderated cold, early multicellular life encountered renewed stress, though not the global isolation of prior ice worlds. Environmental variability, in combination with ongoing chemical and biological adjustments, continued to shape the direction of evolution. The Gaskiers event occupies a subtle place in Earth's history, bridging the era of deep freezes and the forthcoming expansion of animal life. Its influence measured not by total coverage of ice, but by its timing within a world already transformed by earlier extremes. The advance of ice into tropical latitudes did not occur by chance. It emerged from the quiet alignment of several structural forces, each subtle on its own, yet powerful when combined. Continents, atmosphere, and sun formed a shifting geometry that predisposed the planet to instability. During cryogenian time, continental fragments occupied positions close to the equator. When landmasses cluster in low latitudes, they intercept intense solar radiation and experience vigorous rainfall driven by equatorial circulation. Warm air rises, moisture condenses, and precipitation falls in abundance. On these exposed surfaces, chemical weathering proceeds efficiently. Silicate minerals react with carbon dioxide dissolved in rainwater, forming bicarbonate ions that rivers carry to the sea. Over extended timescales, this process draws carbon dioxide out of the atmosphere and locks it into marine sediments. The placement of continents in the tropics therefore amplifies the rate at which atmospheric carbon dioxide can be removed. Unlike high-latitude landmasses, which receive less intense solar input and often host colder, drier climates, equatorial continents function as effective chemical regulators. When extensive tropical land area is present, the capacity for greenhouse gas drawdown increases significantly. In the Cryogenian, the breakup of Rodinia exposed vast new surfaces near the equator, enhancing this removal process. At the same time, solar luminosity was slightly weaker than today. Although the difference was modest on a human scale, over geological periods, even small variations in solar energy influence the equilibrium temperature of the planet. With less incoming radiation to begin with, Earth depended more heavily on greenhouse gases to maintain temperate conditions. A reduction in atmospheric carbon dioxide therefore had proportionally greater impact under a fainter sun than it would in later eras. The carbon cycle itself exhibits inherent sensitivity. Volcanic outgassing introduces carbon dioxide continuously, yet the rate can vary with tectonic activity. Weathering responds to climate conditions, accelerating in warm, wet environments and slowing in cold, dry ones. When continental configuration enhances weathering efficiency, carbon dioxide concentrations may decline below thresholds required to sustain stable warmth. If cooling begins and ice expands, reflective surfaces increase, reinforcing the temperature drop through albedo feedback. Tropical ice is especially consequential because it interrupts the regions where solar energy is most intense. Normally, heat absorbed at the equator drives atmospheric and oceanic circulation that transports energy poleward. When ice intrudes into these low latitudes, the capacity of the planet to redistribute warmth diminishes. The system loses a central stabilizing influence. Under such circumstances, a relatively small initial cooling can cascade into broader glaciation. None of these factors alone necessitates a snowball Earth outcome. Continental positioning, solar output, carbon cycle fluxes, and feedback processes each fluctuate within bounds that usually maintain equilibrium. Yet, in cryogenian time, their convergence appears to have pushed the system toward a threshold. Tropical land enhanced carbon dioxide drawdown. Solar luminosity provided less surplus energy. Carbon cycle feedbacks amplified initial cooling. Ice-albedo reinforced expansion once it began. Thus, ice reached the tropics not as an isolated anomaly, but as the expression of structural alignment. The geography of continents, the chemical exchange between rock and air, and the faintness of the young sun combined to narrow the margin for stability. In that narrowed margin, cooling progressed until reflective surfaces spread across latitudes where they rarely persist. The result was a planet whose climatic architecture allowed even its warmest regions to succumb to frost. The deep freezes of the distant past stand apart from the climates that followed. In the hundreds of millions of years since the Cryogenian, Earth has cooled and warmed many times, yet it has not returned to a state where ice plausibly sealed nearly the entire surface. The reasons lie not in a single protective mechanism, but in gradual shifts that altered the planet's baseline stability. The sun itself has changed. Stellar evolution causes luminosity to increase slowly over geological time. Compared with the faint solar output of 2 billion or even 700 million years ago, the modern sun delivers noticeably more energy to Earth. That additional input raises the threshold at which greenhouse gas reductions can trigger global glaciation. Under a brighter sun, the climate system begins from a warmer equilibrium, making it harder for reflective feedbacks alone to overcome incoming radiation across tropical latitudes. The biosphere has also transformed the carbon cycle into a more intricate and responsive network. During early Earth history, microbial communities influenced atmospheric composition, yet the feedbacks were relatively simple. As complex life evolved, especially after the spread of land plants, biological processes became deeply integrated with weathering and nutrient cycling. Root systems penetrate rock, enhancing chemical reactions that consume carbon dioxide. At the same time, vegetation stabilizes soils and influences hydrology, regulating how quickly minerals are exposed and eroded. Forests, once established across continents, altered the exchange between atmosphere and surface in enduring ways. Through photosynthesis, plants draw down carbon dioxide, yet through respiration and decay they return it. This continuous cycling operates alongside long-term geological sequestration. The interplay between organic carbon burial, carbonate formation, and volcanic outgassing became more buffered as ecosystems diversified. Feedback loops tightened, distributing imbalances across multiple pathways rather than allowing extremes to escalate unchecked. Weathering processes themselves grew more sensitive to biological mediation. The presence of complex plant communities increases the responsiveness of silicate weathering to climatic shifts. In warm, humid conditions, vegetation enhances mineral breakdown. In colder or drier intervals, reduced biological activity slows it. This coupling between temperature and weathering creates a stabilizing feedback that tends to moderate large swings. While not immune to disturbance, the system resists transitions toward full planetary freeze more effectively than in earlier eras. Atmospheric regulation improved further through the accumulation of oxygen and the diversification of life forms capable of influencing gas composition. The modern atmosphere contains a mix of greenhouse gases maintained within ranges shaped by both biology and geology. Variations occur, and significant ice ages have unfolded during the Phanerozoic, yet these have remained partial, confined to higher latitudes. Even during the late Paleozoic or the Quaternary, equatorial oceans remained largely ice-free, preserving the fundamental circulation patterns that distribute heat. Plate tectonics continues to rearrange continents, and carbon fluxes still fluctuate. The possibility of extreme cooling cannot be dismissed entirely over vast timescales. However, the combination of brighter solar output and a more interconnected biosphere has shifted the climate system away from the fragile balance that once allowed tropical ice to spread. Thresholds that were reachable in the Cryogenian now lie further from the present baseline. Thus, the absence of another global ice world reflects cumulative change rather than simple luck. The sun's gradual brightening, the rise of complex plants, and the tightening of carbon cycle feedbacks have collectively increased the resilience of Earth's climate. Cold chapters remain part of the story, but the conditions that once permitted nearly planetary freeze have grown less accessible as the world matured into a more regulated state. Cold returned to Earth more than once after the Cryogenian, yet it returned in a different form. Instead of sealing oceans beneath reflective armor from equator to pole, later ice ages unfolded within a climate system that retained open seas and active circulation. The contrast is clearest in the late Paleozoic Ice Age, a prolonged interval of cooling that began in the late Carboniferous and extended into the early Permian. During this time, the southern supercontinent Gondwana drifted across high latitudes. Vast regions of what are now South America, Africa, Antarctica, Australia, and India lay near the South Pole. Continental positioning played a decisive role, yet unlike earlier configurations that placed landmasses in tropical belts, Gondwana's polar alignment localized the most severe cooling. Ice sheets expanded over southern continents, carving valleys and depositing glacial sediments that remain visible in outcrops across these regions. Striated bedrock and dropstones within marine sequences attest to significant ice advance, but their distribution reflects hemispheric concentration rather than global enclosure. The Carboniferous world differed in another critical respect. Forests had spread widely across tropical lowlands, forming dense coal swamps. Vascular plants with deep root systems and woody trunks had become major agents within the carbon cycle. Through photosynthesis and burial of organic material, these forests drew large amounts of carbon dioxide from the atmosphere. Extensive peat accumulation eventually formed coal deposits, effectively sequestering carbon and reducing greenhouse warming. This biological drawdown contributed to global cooling, yet the presence of complex vegetation also modulated feedbacks in ways absent during Snowball Earth intervals. Ocean circulation during the late Paleozoic remained vigorous. Although glaciation influenced sea level and regional climates, equatorial oceans stayed largely ice-free. Heat transport between low and high latitudes persisted, preventing the runaway albedo feedback that characterizes ice world states. Seasonal contrasts intensified in some regions, and glacial and interglacial cycles likely oscillated in response to orbital variations, yet the system never tipped into a fully reflective equilibrium. The atmosphere of the Carboniferous also contained higher oxygen concentrations than today, a consequence of widespread organic carbon burial. This altered both ecological conditions and fire regimes, yet it did not destabilize the greenhouse balance in the same manner as early methane loss or massive tropical weathering had done in the Cryogenian. Instead, cooling during the late Paleozoic unfolded within a framework shaped by abundant life and a brighter sun, limiting its geographical reach. Sea levels fluctuated dramatically as ice sheets waxed and waned across Gondwana, creating cyclothems in sedimentary basins far from the poles. Coastal habitats expanded and contracted in rhythmic response. Despite these shifts, tropical marine ecosystems continued to flourish, and biodiversity diversified across both marine and terrestrial realms. Glaciation imposed stress and reorganization, but not planetary suspension. The distinction lies in scale and feedback structure. Snowball Earth states relied on tropical ice expansion and weakened solar input to amplify cooling globally. In contrast, the late Paleozoic Ice Age represented a polar-focused glaciation within an otherwise dynamic, interconnected climate system. Ice sculpted continents and lowered sea levels, yet blue oceans persisted, and sunlight continued to warm equatorial waters. Later ice ages demonstrate that cold chapters need not culminate in total enclosure. They reveal a planet capable of sustaining prolonged glaciation while maintaining circulation, biodiversity, and regional warmth. In this contrast between hemispheric ice and global freeze, Earth's evolving climate architecture becomes visible, shaped by tectonics, biology, and solar change in ways that prevent repetition of its most extreme frozen states. Even now, beneath familiar skies and open oceans, Earth remains within an ice age. The present chapter belongs to the Quaternary, an interval that began about 2.6 million years ago, when large continental ice sheets once again established themselves in the northern hemisphere. Greenland and Antarctica hold persistent reservoirs of frozen water, anchoring the climate in a state defined by permanent polar ice, even as temperate regions experience warmth and seasonal change. This ice age does not resemble the deep freezes of the Cryogenian. It unfolds through oscillations rather than planetary enclosure. Over tens of thousands of years, massive ice sheets advance across North America, Northern Europe, and Siberia, then retreat, then advance again. These rhythms arise from subtle variations in Earth's orbit and axial tilt, known collectively as Milankovitch cycles. Changes in the shape of Earth's orbit, the angle of its tilt, and the wobble of its axis alter how sunlight is distributed across latitudes and seasons. When summers in the high northern latitudes grow cooler, winter snow survives longer, and ice sheets gradually thicken. When summer insolation increases, melting accelerates and glaciers withdraw. The result is a pattern of glacial and interglacial phases. During glacial maxima, sea levels fall by more than 100 meters as water becomes locked within continental ice. Coastlines shift outward, exposing vast continental shelves. During interglacials, like the one currently underway, ice recedes toward higher latitudes and sea levels rise. These transitions occur over timescales of tens of thousands of years, a pace rapid in geological context yet slow in human perception. Despite the impressive scale of quaternary ice sheets, equatorial oceans remain ice-free. Tropical temperatures moderate global climate through continuous absorption of solar energy and transport of heat via ocean currents and atmospheric circulation. The reflective feedbacks that once allowed ice to approach equatorial latitudes do not engage fully under the brighter, modern sun and the complex carbon cycle maintained by a diverse biosphere. Even at the height of the last glacial maximum, around 20,000 years ago, the tropics preserved open water and active hydrology. Carbon dioxide concentrations also fluctuate during quaternary cycles, decreasing during glacial phases and rising during interglacials. Ice core records from Antarctica reveal these variations clearly, with carbon dioxide and temperature tracking closely together. Yet, the magnitude of these changes remains far below the extremes inferred for cryogenian events. The climate system oscillates within a narrower band, buffered by robust feedbacks and sustained equatorial warmth. Living within this ongoing ice age situates humanity within a dynamic climate framework. The presence of polar ice shapes, ocean circulation, influences atmospheric patterns, and governs sea level. Glacial legacies remain visible in landscapes carved by ice and in sediment deposited by meltwater rivers. At the same time, the stability of open oceans and persistent tropical heat prevent descent into a global freeze. The Quaternary reminds us that an ice age need not envelop the entire planet. It can exist as a condition defined by enduring polar ice and cyclical advance and retreat, moderated by orbital mechanics and atmospheric composition. The world outside our windows occupies one interlude within that longer pattern, an interval of relative warmth framed by colder epochs before and after. Compared to the silent, reflective expanses of Snowball Earth, our present ice age is measured and partial, marked by rhythm rather than total stillness. Speculation about the future often begins in silence, in the space between what has happened before and what might unfold again. Earth has entered states of profound cold, yet it now orbits a star that grows slowly brighter with time. The long-term increase in solar luminosity shifts the baseline from which climate variations operate. Each million years adds a subtle increment of energy to the system, raising the threshold that greenhouse gases must fall below before widespread glaciation can take hold. This gradual brightening does not eliminate variability. Plate tectonics continues to rearrange continents, altering ocean gateways and weathering patterns. Over tens to hundreds of millions of years, supercontinents will assemble and fragment again, redistributing land across latitudes. If large continental areas were to occupy equatorial regions, enhanced chemical weathering could draw down atmospheric carbon dioxide, cooling the climate. Yet the brighter sun offsets part of that effect, requiring more extreme carbon dioxide reduction than in the distant Cryogenian to initiate runaway freezing. The carbon cycle remains a central regulator, linking volcanic outgassing, weathering, biological productivity, and sediment burial. Its sensitivity is evident in past climate swings. Rapid reductions in greenhouse gases could, in principle, drive significant cooling. However, modern Earth hosts complex biospheric feedbacks that modulate these processes. Land plants influence mineral breakdown, soil formation, and organic carbon storage. Marine organisms participate in carbonate production and burial, shaping the alkalinity of seawater. These interconnected pathways distribute imbalances through multiple channels, reducing the likelihood that a single perturbation will escalate unchecked. Plate tectonics introduces uncertainty through its inherent unpredictability. Subduction zones generate volcanic emissions that replenish carbon dioxide, while mountain building enhances weathering by exposing fresh rock. The rates of these processes fluctuate over geological intervals. In theory, an unusual combination of reduced volcanic outgassing and intense tropical weathering could lower carbon dioxide sufficiently to promote substantial glaciation. Yet such a scenario would have to overcome the moderating influence of higher solar input and the stabilizing feedbacks of a mature biosphere. Orbital variations will continue to drive glacial and interglacial cycles within the current Ice Age framework. Over hundreds of thousands of years, ice sheets will advance and retreat in response to shifts in tilt and eccentricity. These cycles may grow stronger or weaker, depending on atmospheric composition. Still, their scope remains constrained to partial glaciations rather than global freeze, provided greenhouse gas concentrations remain within certain bounds. Long-term climate models that incorporate projected solar brightening and carbon cycle feedbacks generally indicate that a return to snowball Earth conditions is highly improbable under natural processes alone. The energy balance of the system has shifted since the Cryogenian. For tropical oceans to freeze today, atmospheric carbon dioxide would need to fall to levels far below those typical of recent geological history, and sustained feedbacks would have to amplify cooling beyond the moderating capacity of equatorial heat transport. Uncertainty is inherent in any forecast extending millions of years into the future. Continents will drift, volcanic arcs will emerge and vanish, and biological evolution will continue to reshape atmospheric chemistry. Yet within the context of current understanding, the convergence of factors that once permitted near global ice coverage appears unlikely to recur. The planet has matured into a configuration where thresholds for complete freeze lie further from the present state. Thus, the question of recurrence resolves into a measure of probability rather than inevitability. Earth retains the capacity for significant climatic swings, but the structural conditions that enabled tropical ice to spread across its surface have diminished. In the quiet calculus of solar evolution, tectonic motion, and carbon cycling, the balance now favors resilience over repetition of the deepest freeze. Within the quiet strata of cryogenian rock, two interpretations rest side by side. Both accept that ice spread far beyond familiar limits, yet they differ in how completely the oceans were enclosed. The Snowball Earth model envisions a planet almost entirely sealed beneath thick ice, its seas capped from pole to near equator, its surface reflecting sunlight with relentless efficiency. The slushball alternative proposes a more nuanced state, one in which substantial ice covered much of the globe, while belts of open or seasonally thin water persisted near the tropics. The distinction matters because it shapes how feedbacks operated and how life endured. A complete freeze implies that ocean surface circulation ceased almost entirely and that atmospheric exchange with seawater was drastically curtailed. In such a world, deglaciation would require immense accumulation of greenhouse gases before warming could overcome global albedo. The geological pairing of extensive glacial deposits with thick cap carbonates appears consistent with that scale of reversal. Carbon isotope anomalies and sedimentological patterns have been cited as further support for a world locked in near total ice. Yet other observations invite restraint. Some sedimentary sequences preserve features that may indicate episodic open water or thinner ice at low latitudes. Evidence of wave-influenced structures in certain cryogenian strata suggests that at least localized areas were not permanently sealed. Certain geochemical signatures imply ongoing exchange between ocean and atmosphere that might have been difficult under a completely frozen lid. Climate models also show that equatorial regions can, under some parameter settings, retain narrow open water bands even while high latitudes remain icebound. Paleomagnetic data confirming low-latitude glacial deposition are robust, yet they do not specify the continuity of ice cover across oceans. The difference between continent-spanning glaciers and uninterrupted sea ice is subtle in the rock record. Diamictites and dropstones demonstrate cold conditions and ice transport, but they cannot alone determine whether tropical oceans were universally capped or intermittently exposed. Climate simulations add further texture to the debate. Models incorporating ice-albedo feedback often produce globally frozen states once thresholds are crossed, especially under lower solar luminosity and reduced carbon dioxide. However, the inclusion of ocean heat transport, cloud feedbacks, and dynamic ice sheets can yield partially open configurations. The complexity of these models reflects the sensitivity of the climate system to interacting variables rather than a simple binary outcome. Uncertainty in this context does not indicate weakness of understanding, but rather the limits imposed by deep time. Rocks preserve fragments of past conditions, and interpretation requires integrating sedimentology, geochemistry, paleomagnetism, and modeling. Each dataset carries assumptions and margins of error. When different lines of evidence converge, confidence grows. When they diverge, hypotheses adapt. The snowball versus slushball conversation illustrates how science accommodates nuance. Both perspectives acknowledge profound glaciation. They differ in degree and mechanism. Over time, refinements in dating techniques, isotopic analysis, and numerical simulation continue to narrow uncertainties, yet some ambiguity may remain inherent to events that occurred hundreds of millions of years ago. In this dialogue between models and stone, the focus remains on structure and feedback rather than certainty alone. The cryogenian freezes were extreme by any measure. Whether oceans lay fully imprisoned beneath kilometers of ice or retained narrow equatorial windows, the essential insight endures. Earth entered states of cold far beyond modern experience. The debate itself reflects a discipline attentive to detail, willing to hold multiple possibilities while evidence accumulates, and comfortable with the measured evolution of understanding. Long before rock layers are drilled or isotopes are measured, another kind of landscape is built inside equations. In laboratories and research centers, frozen planets first take shape as numbers moving across screens, representations of atmosphere, ocean, ice, and sunlight, woven into climate models. These simulations do not recreate the past in perfect detail, yet they allow scientists to explore how feedbacks unfold when certain thresholds are crossed. At the heart of many models lies a simple balance. Incoming solar radiation warms the surface, while outgoing infrared radiation cools it. The difference between these flows determines whether the planet gains or loses heat. Ice introduces a powerful modifier to that exchange. Bright surfaces reflect a significant portion of sunlight back to space, reducing the energy absorbed by darker land or water. As ice expands, planetary reflectivity increases. In model language, albedo rises. Simulations reveal that this reflectivity does not scale gently. When ice reaches lower latitudes, particularly near the tropics, a critical point can be approached. Because equatorial regions receive the most sunlight, covering them with reflective ice sharply reduces absorbed energy. Models show that once ice advances beyond certain latitudinal bands, additional cooling accelerates rapidly. The system transitions from gradual expansion to what is termed a runaway state, in which ice spreads toward global dominance. These runaway scenarios depend on initial conditions. Parameters such as atmospheric carbon dioxide concentration, solar luminosity, continental configuration, and ocean heat transport influence where thresholds lie. Sensitivity experiments adjust one variable at a time, allowing researchers to test how resilient the climate is under different assumptions. Lowering carbon dioxide incrementally, for example, demonstrates how greenhouse reduction can tip a marginally stable climate into sustained freezing when combined with high albedo. Ocean circulation plays a stabilizing role in many simulations. Warm currents transport heat from equator to pole, moderating extremes. When models reduce ocean heat transport efficiency, equatorial regions cool more readily, making runaway states easier to achieve. Conversely, strong circulation can maintain narrow belts of open water even when higher latitudes remain ice-covered. In such configurations, slushball conditions persist instead of complete freeze. Cloud feedback introduces additional complexity. Clouds can reflect sunlight, enhancing cooling, or trap infrared radiation, contributing to warming. How cloud cover responds to expanding ice influences whether reflectivity thresholds are crossed abruptly or gradually. Different modeling frameworks treat these feedbacks in distinct ways, leading to variation in predicted outcomes. Rather than a single answer, simulations provide a range of plausible trajectories, each contingent on specified inputs. Importantly, modeling does not replace geological evidence, but complements it. The rock record establishes that severe glaciations occurred. Models test whether known physics can reproduce conditions consistent with those records. When simulations yield global freeze under cryogenian solar luminosity and plausible greenhouse concentrations, confidence grows that the mechanisms are physically feasible. When parameters must be stretched unrealistically to produce total ice cover, interpretations shift. Modeling a frozen planet thus becomes an exercise in exploring boundaries. It clarifies how sensitive Earth's climate can be to incremental change and where feedback loops intensify. At the same time, It underscores that runaway states require specific alignments of variables. Through iterative refinement and comparison with empirical data, climate models deepen understanding without claiming absolute reconstruction. In these digital experiments, the frozen Earth emerges not as an abstract legend, but as a system governed by energy balance, reflectivity, and feedback structure. Equations outline the conditions under which ice advances or retreats, offering insight into both ancient extremes and the resilience that prevents such states from arising easily in the present configuration. Imagine a vantage point far beyond the reach of clouds or orbiting satellites, where Earth appears not as a landscape, but as a disk suspended in blackness. During its deepest freezes, that disk would have looked profoundly different. The familiar swirls of blue ocean and drifting cloud would have given way to a nearly uniform pallor, a world dominated by light reflected rather than absorbed. From such a distance, the planet's most striking feature would be its brightness. Ice and snow possess high reflectivity, and when they extend across continents and oceans alike, the overall albedo of the planet rises dramatically. Sunlight striking the surface would scatter outward in a cold sheen, making Earth gleam against the dark. The contrast between illuminated hemisphere and shadow would appear sharp, yet the illuminated side itself would seem muted, its whiteness absorbing little warmth. Above this frozen surface, the atmosphere would form a thin, luminous arc at the planet's edge. Even in extreme cold, air does not vanish. It clings to the globe as a delicate halo, scattering sunlight into a faint gradient from blue to pale gray along the limb. In a snowball configuration, reduced water vapor and altered cloud distributions might render this halo clearer, perhaps thinner in appearance, though still present. The breath of gases would remain, even as the surface beneath grew silent. The sun, viewed from such an era in deep time, would appear slightly dimmer than it does today, its output incrementally lower. That modest reduction, insignificant on a human timescale, contributed to the vulnerability of the climate system. Yet from space, the sun's face would still burn steadily, casting its rays upon an Earth that now returned much of that energy unclaimed. The interplay between incoming light and reflective surface would define the planet's outward appearance. Where oceans once shimmered, dark and heat-absorbing, sheets of sea ice would now stretch uninterrupted across vast distances. The subtle tonal variations of liquid water would be replaced by textures of frozen expanse. Fractures and ridges might scar the ice where stresses accumulated, but from afar, these details would blur into uniform brilliance. The equatorial belt, typically a band of deep blue, would fade into the same pale spectrum as higher latitudes, erasing familiar climatic gradients. Yet the image would not be entirely still. Volcanic plumes would rise intermittently through the white surface, thin columns of ash and gas ascending into the atmosphere. Along subduction zones and rift systems, eruptions would punctuate the quiet, with transient marks of darker material settling upon ice. These plumes, small at planetary scale, would nevertheless signify internal heat persisting beneath the frozen shell. From orbit, they would appear as faint smudges, reminders that the planet's interior remained active. Clouds might drift in sparse formations, their brightness difficult to distinguish against the reflective ground. Storm systems would exist, though altered in character, their moisture limited and their contrasts subdued. The dominant impression would be one of uniformity, a world where color compressed into variations of white and silver. Seen from space, a fully frozen Earth would embody a balance tilted toward reflection. It would radiate back much of the light it received, its climate suspended within a state of luminous austerity. Beneath that gleaming exterior, oceans would endure, continents would persist, and volcanic forces would continue their slow work. The image, serene and stark, would capture a planet in one of its most extreme configurations, defined by light turned outward into the surrounding dark. Frozen worlds are not rare in the universe. When astronomers peer beyond our solar system, they find planets orbiting distant stars at a range of temperatures, many of them likely locked beneath global ice. Against that wider backdrop, Earth's ancient freezes become more than episodes of climate. They become lessons about what allows a world to remain habitable at all. Habitability depends not only on distance from a star, but on the delicate balance between incoming energy and the atmosphere's capacity to retain it. Earth resides within a zone where liquid water can exist, yet that condition is not guaranteed. The Cryogenian record shows how feedback loops can narrow the margin between ocean and ice. A modest reduction in greenhouse gases, combined with high reflectivity, can shift the balance dramatically. Once reflective surfaces spread, cooling accelerates, and the system resists reversal until opposing forces accumulate. This interplay between feedback and stability extends beyond Earth. Mars provides a nearby example of how climate pathways diverge. Geological evidence indicates that early Mars may have possessed liquid water flowing across its surface. Valley networks and sedimentary deposits suggest a warmer past, yet without sustained volcanic outgassing or a sufficiently thick atmosphere, Mars lost much of its greenhouse capacity. As its internal heat diminished and its atmosphere thinned, the planet crossed a threshold into persistent cold. Today, water remains largely locked in ice or subsurface reservoirs, and surface temperatures rarely permit melting. Earth avoided a similar fate not by accident, but through an active carbon cycle and ongoing tectonic renewal. Volcanic emissions replenish atmospheric carbon dioxide over long timescales, counteracting weathering losses. Subduction recycles carbonates, linking crust and mantle in a continuous exchange. Biological processes further complicate and stabilize these exchanges. The presence of liquid water itself facilitates feedbacks that regulate temperature, enhancing weathering in warm conditions and slowing it when cooling sets in. Exoplanet surveys reveal many planets likely orbiting within their stars' habitable zones. Yet being positioned at an appropriate distance does not ensure long-term surface water. A planet with high reflectivity, perhaps due to extensive ice or cloud cover, can remain cold even within that zone. Conversely, a dense greenhouse atmosphere can drive runaway warming. Climate models adapted for exoplanets explore these possibilities, testing how variations in atmospheric composition, rotation rate, and land distribution influence equilibrium states. Ice, therefore, serves as a teacher of planetary boundaries. It demonstrates that habitability is not a static property, but an emergent outcome of interacting feedbacks. Earth's own history shows that a world can tip toward extensive freezing and still recover, provided that energy sources and carbon reservoirs persist. The capacity for recovery depends on internal heat, atmospheric composition, and the absence of irreversible feedbacks. When scientists analyze light spectra from distant planets, searching for hints of water vapor or oxygen, they consider not only chemistry but climate stability. A habitable world must resist extremes long enough for liquid water to endure. The Earth's Ice World chapters illustrate how resilience arises from layered regulatory systems rather than singular factors. Viewed in this broader context, the frozen intervals of deep time expand perspective. They show that even a life-bearing planet can approach climatic edges, yet also that recovery is possible when feedbacks remain balanced. Habitability emerges as a fragile but dynamic equilibrium shaped by stellar input, atmospheric composition, geology, and biology working together over immense spans of time. Survival is not always loud. In Earth's coldest chapters, it unfolded quietly, beneath layers of ice and within thin margins of chemical warmth. When continents stood rimmed with glaciers and oceans lay capped by frozen ceilings, life did not vanish in a single sweep. It narrowed, retreated, adjusted. Its persistence reshaped the meaning of habitability itself. Microbial life, already ancient by the time of the deepest freezes, possessed traits suited to endurance. Many microorganisms can enter dormant states, slowing metabolism to near stillness when nutrients dwindle or temperatures fall. Cells alter membrane composition to remain functional in cold environments. Proteins adapt to operate at lower temperatures, maintaining biochemical reactions where warmth is scarce. These adjustments are not dramatic in isolation, yet across immense spans of time, they allow continuity where more complex systems might collapse. Beneath ice-covered oceans, hydrothermal vents continued to release mineral-rich fluids from the seafloor. These environments offered chemical gradients independent of sunlight. Microbial communities capable of chemosynthesis could draw energy from compounds such as hydrogen sulfide or methane, supporting ecosystems that did not rely on photosynthesis at the surface. In subglacial pockets and within porous rock, other microorganisms likely endured in protected niches, shielded from surface extremes. Pressure can refine rather than extinguish. Evolution under constraint often selects for efficiency and flexibility. When environmental conditions fluctuate or compress into narrower bands, organisms that tolerate broader ranges gain advantage. Genetic variation accumulates gradually, and lineages capable of exploiting small opportunities persist. Over successive generations, these subtle shifts can produce new metabolic pathways, structural innovations, or symbiotic relationships. The rise of more complex life after Cryogenian freezes suggests that extreme stress did not halt evolutionary potential. Instead, it may have filtered and reorganized biological communities. Post-glacial environments offered nutrient pulses and altered chemical conditions, creating openings for diversification. Organisms that survived the cold entered a transformed world, one in which ecological space expanded. The capacity to endure extremes may have primed certain lineages for experimentation when conditions stabilized. Microbes remain the foundation of this narrative. Their adaptability underpins Earth's resilience. They inhabit boiling springs and polar ice, deep subsurface fractures and ocean vents. Their metabolic diversity extends across chemical possibilities far beyond those of animals and plants. During frozen epochs, this versatility likely provided continuity, ensuring that basic biological processes persisted even when surface ecosystems diminished. Resilience in this context does not imply invulnerability. Many lineages surely disappeared, and genetic bottlenecks would have shaped surviving populations. Yet extinction was not absolute. Life's architecture, grounded in simple cellular forms and flexible metabolisms, allowed it to contract and later expand. The record in sedimentary layers, microfossils, and isotopic signatures testifies to continuity across intervals that appear, at first glance, hostile to persistence. In reflecting on these frozen chapters, a gentle shift emerges. Survival is not measured solely by dominance or abundance, but by continuity through adversity. Earth's biosphere has weathered global cold, rebalanced chemistry, and adjusted to changing energy flows. The adaptability of its smallest inhabitants ensured that, even when ice defined the planet's surface, the processes of life continued beneath. From those quiet refuges, complexity eventually returned, shaped by pressures that once seemed insurmountable. When the timeline of Earth is stretched across billions of years, a pattern begins to reveal itself, not as repetition in exact detail but as rhythm. Warmth gives way to cold, seas advance and retreat, atmospheres shift, continents gather and part. Stability appears not as a permanent state but as an interval between adjustments. The deep freezes are only one expression of that larger dynamism. The rock record preserves these fluctuations in layered form. Glacial deposits sit above tropical sediments, marine limestones overlie evidence of ice. Chemical signatures oscillate between states that imply warmth and those that mark cooling. None of these phases lasts indefinitely. Each emerges from the interaction of tectonics, solar evolution, atmospheric chemistry, and biological innovation. Earth's climate is not a fixed setting, but a responsive system capable of crossing thresholds and then rebalancing. Over immense spans of time, the sun brightens, altering the baseline upon which climate variations occur. Plate tectonics rearranges continents, redirecting ocean currents and influencing weathering rates. Volcanic arcs rise and subside, adjusting the flow of greenhouse gases into the atmosphere. Life itself modifies the air and oceans, introducing new feedbacks that were absent in earlier eras. Through all of this, the system oscillates, sometimes gently, sometimes dramatically. The Ice World episodes fit within this larger arc as moments when feedbacks amplified beyond familiar limits. They were not random interruptions, but consequences of conditions converging. Likewise, the warmer greenhouse intervals that bracket them arose from different alignments of variables. Neither extreme defines Earth in isolation. Instead, both demonstrate the capacity of a planetary system to shift under changing internal and external influences. This recurring instability does not imply chaos. The climate operates within physical laws that constrain its behavior. Energy balance, atmospheric composition, and ocean circulation obey predictable relationships. Yet within those constraints, outcomes vary depending on configuration. The sensitivity of the system to feedback loops means that small shifts can cascade when thresholds are crossed. Over deep time, such cascades have recurred, though never in precisely the same way twice. As continents continue to drift and mountains rise, the climate will evolve further. Future assemblies of land could alter carbon cycling. Future volcanic regimes could adjust atmospheric chemistry. The sun's gradual brightening will continue to reshape the planet's habitable window. In this context, the frozen chapters become part of a longer narrative of transformation rather than isolated curiosities. What emerges is a view of Earth as a dynamic entity, its surface and atmosphere continually negotiating balance. Oceans freeze and thaw, not because the planet is unstable in a chaotic sense, but because it is responsive. Feedbacks operate, sometimes stabilizing, sometimes amplifying. Through it all, geological and biological processes remain intertwined, shaping one another across epochs. The pattern across deep time is therefore one of movement rather than stasis. Climate swings, continental migrations, and atmospheric shifts form a woven history of change. The ice worlds stand as luminous markers within that weave, reminders that even extremes are chapters within an ongoing story of planetary adjustment. In tracing these chapters, the narrative begins to settle toward reflection. holding the awareness that Earth's history is defined less by permanence than by transformation, sustained over unfathomable durations. From a distance measured in billions of years, the ice worlds no longer appear as catastrophes alone. They settle into the long cadence of a planet that shifts, recalibrates, and continues. The frozen chapters were immense, luminous with reflected light, yet they were not permanent states. Ice advanced, oceans stilled, feedbacks intensified, and still the arc bent back toward balance. Each time the surface grew pale and reflective, forces beneath and above continued their patient work. Volcanoes released invisible gases into the sky. Chemical reactions unfolded at the boundaries between rock and water. Beneath frozen ceilings, currents persisted in shadowed depths, and microbial cells endured within thin layers of liquid. The planet did not stop. It slowed, narrowed, concentrated. When warming returned, it did not arrive as a simple reversal, but as transformation. Ice retreated, oceans shifted in chemistry, nutrients surged, and ecological spaces reopened. The world that followed each freeze was not identical to the one before. Continents had moved, atmospheres had changed, and life had adapted. Recovery did not restore an earlier arrangement. It established a new equilibrium shaped by what had endured. Through this repetition of descent and return, resilience emerges as a defining trait of Earth's history. Resilience does not imply smoothness or constant comfort. It reflects the capacity of interacting systems to absorb disruption and reorganize without losing their fundamental continuity. Tectonics maintained exchange between interior and surface. The carbon cycle adjusted to swings in temperature. Biology persisted, even when confined to refuges difficult to imagine from our vantage point. The frozen intervals also influenced the trajectory of life in lasting ways. Chemical shifts associated with deglaciation altered ocean conditions. Evolution proceeded through bottlenecks and expansions, selecting for traits suited to fluctuating environments. Complex organisms eventually appeared in the wake of these extremes, inheriting a planet whose systems had been tested at their limits. The world we inhabit carries the imprint of those ancient calibrations. Earth's climate has never been perfectly steady. It oscillates across scales, sometimes subtly, sometimes dramatically, yet within that variability lies an underlying continuity of process. Energy flows from the sun, heat radiates to space, elements cycle through rock, water, air, and living tissue. When one pathway strengthens or weakens, others respond. The balance shifts, but rarely collapses beyond recovery. Seen in this light, the ice worlds become chapters in a broader meditation on planetary endurance. They demonstrate that even profound environmental change need not erase the conditions for life entirely. Instead, life contracts and waits, systems adjust, and thresholds are eventually crossed in the opposite direction. The surface brightens and dims across eras, while beneath, exchange and transformation continue. The present world is shaped by that deep memory. Oceans circulate under a brighter sun. Continents occupy new configurations. Forests and cities stand where ice once lay in other ages. The resilience embedded in Earth's long history informs the stability we experience, even as change remains inherent. A planet that freezes and then thaws carries both vulnerability and strength within its record. The frozen intervals were temporary, their influence endures. In the quiet span of geological time, survival is measured not in unbroken calm, but in the return to balance after extremes. Earth has crossed that distance before, emerging altered yet alive, its story continuing without haste. guided by forces that have sustained it through ice and into warmth once more.